Hi everyone, welcome to the next section in polynomials. In this section we are finally going to deal with equations. We have an equal sign here and that's the whole goal, is to actually solve equations that involve polynomials, so now we get to finally do that. Step number one, set the equation equal to 0. This one is not equal to 0, so we're going to move this 3x over here and set this equal to 0 to begin with. So let's do that. Next step is to factor. So look at your terms in your polynomial and see, is there something common that you can factor out of all three terms? And there is. Each one of these terms has an x in it. So let's factor out that x. Okay, now this is really helpful because now I have a quadratic. And so at this point, I can see if I can factor this quadratic. And I can factor this. Even though it's got a coefficient of 2, if I remember how to factor, that would be really helpful. Remember, if you can't or if you don't like factoring these, although factoring is easier, you can always use the quadratic formula. But I'm going to review factoring just to help you with that. And that's how we're going to get our solutions. So remember, our first step here is to multiply 2 times -3. That's -6. And now I'm going to look for factors of -6 that add up to -5, and it's -6 and +1. So -6 and 1 are my two factors, and I am going to rewrite this now, and I'm going to split this middle term into two terms, -6x plus 1x. Okay, I've rewritten it, splitting that middle term. Now I'm going to divide it in half and factor out each half. Okay, I've done that, and from that, there's my factors. 2x plus 1 times x minus 3 plus this x over here. So let's list out all those factors. This is this polynomial in factored form. Now I'm looking for my values of x that would make this 0. This one, this x, would be 0. This one would be -1/2. And this one would be +3. So my three solutions are x equals 0, -1/2, and 3. And those are my three solutions to this equation. Why did I have 3 zeros? Because this was a cubic polynomial. That tells you how many solutions you're going to have in total. Here's another equation. Let's walk through this again. We need to set it equal to 0 first, so I need to move this over. Notice when I moved it over, I put it in the middle so that it would be in standard form. Now I'm going to look for the greatest common factor to these terms, and I see that all of them can be divided by 3 and an x squared. So I'm going to factor out 3x squared. Okay, I've factored out my 3x squared, and now I'm left with a quadratic, and this looks easy. So let me try to find two factors of +4, which will add up to be -2. 2 times 2, 4 times 1. This is not going to work. So I can't factor. I have to use my quadratic formula. So use the quadratic formula for this. So x equals -b is +2 plus or minus the square root of b squared minus 4 times a times c all over 2a. There we go. Now simplify this. This is -12. So now I'm going to simplify all of this. 12 is 4 times 3, so I took out that -4 here, became 2i less square root of 3, and here are two of my solutions. I can still simplify this further, because this term, and this term can all be divided by 2. So I want to do that. When you divide that, this has to divide with the coefficient, not the square root. The square root is, think of it as a variable tagging along. When you are simplifying, it's just these numbers that you deal with. So this simplifies to be this. And it is 1 plus or minus I square root of 3. These are two of your solutions. These are not factors, these are solutions. When you use the quadratic formula, you will get the zeros. So 1 plus I square root of 3, or square root of 3i, is one solution. The other is 1 minus square root of 3i. Those are two of the solutions. The third and fourth solution come from here because this is 3x squared, so you have 0 as a solution here. And because that's an x squared, actually 0 has a multiplicity of 2. So you have 0, 0, and 0 with a multiplicity of 2, and 1 plus or minus square root of 3i, and those are your 4 solutions for this one. So in the first one we factored, in this one we used the quadratic formula to find our solutions. Here's another example, which is pretty nice because they've already factored it for us, and all they want to know is what are the real or imaginary solutions of this. So since they've done part of the factoring, let's go ahead and finish. This is a difference of 2 squareds. X squared is a perfect square, and so is 1. So this factors to be x plus 1, x minus 1. This is the sum of 2 perfect squares, not the difference, but the sum. You can factor this the same way, only you have to add the I. So this is x plus 2i, x minus 2i. So now that we have our 4 factors, from our factors we will get our solutions or our zeros. Sometimes they're called roots, whatever they call it, same thing. We'll get our zeros from these. So -1 and +1 are 2 zeros, and -2i and +2i are 2 zeros. So you could write that your solutions are plus or minus 1 and plus or minus 2i. You can feel free, you can list them all 4 out, or you can do it that way. That's perfectly fine, but that's how you would do this one. Okay, must feel like ultimate challenge, but this really isn't that bad. Just wait, we're not done yet. But this is your lesson check question. What are the real or imaginary solutions of this? So set it equal to 0, find your greatest common factor, factor it if possible, use the quadratic equation if you can't, and give me a list of all your zeros. That's your lesson check. Okay, on the bottom of page 297 are 2 factoring patterns that we have not talked about yet and are really important and a challenge to memorize. So please take the time to put these in your notes in a way that you can find them and use them in the future. What I want you to see is how to factor a sum of 2 cubes or a difference of 2 perfect cubes. So in other words, if you have a perfect cube plus a perfect cube, how does that factor? And if you have a perfect cube minus a perfect cube, how does that factor? These are the patterns that are written in your book. This is what you want in your notes. What I'm going to do is walk through this so you can see how it works. I'm going to use this example of 8x cubed plus 1. 8x cubed is 2x times 2x times 2x. So the cube root of this is 2x. So if this is our a cubed, a is 2x. 1 is also a perfect cube. It has a cube root of 1. So we're going to follow this pattern here. Our a is 2x because it's the cube root of this, and our b is 1. So when we factor it, the first part is going to be 2x plus 1, keeping this sign. Then we're going to take our a term of 2x and square it. So this is 4x squared minus 2x times 1, which is just 2x, minus 2x plus b squared, or 1 squared, which is 1. Okay, this could be a bigger number if it wasn't 1, but because it's 1, it's a little easier. But that's how. So here is 8x cubed plus 1 fully factored. Now I'm going to do the same thing with 8x cubed minus 1. What if it's a difference of 2 perfect cubes? So 8x cubed minus 1 would be 2x minus 1 times, now I'm going to square my a, so this is 4x squared plus a times b, or 2x, plus b squared, or 1. And that is the difference of 2 cubes fully factored. So if you want the solutions of this, when you get down to here, you'll have to use the quadratic formula for this solution. This is another type of situation you can come up with in factoring that you haven't seen yet. So still it is set equal to 4, so let's start by setting it equal to 0. Now this looks really confusing because we have an x to the 4th and we have an x to the squared. And so it looks like, how do we do this? But let me show you what it would look like if I rewrote it a little bit. If we wrote it like this, it would be very easy to factor, wouldn't it? We would know it's just x minus 4 times x plus 1, because negative 4 and positive 1 multiply to be negative 4 and add up to be negative 3, right? So this is x minus 4 times x plus 1, and we are all done. This pattern is the same as this. It's the same pattern that we follow, but because this isn't squared, it's x to the 4th, and this isn't a single x, it's x squared, these two are going to be, instead of being single x's, I'm going to double them. This is x squared, like that. So ignore this. This was just to see the pattern. This factors to be that. Do you see how that works? And if you FOILed this, you would end up with this right here. So look for those kind of quadratic patterns that we learned before, and then just make these x squareds instead of single x's. Because they're x squareds, we can factor them further. This factors to be x plus 2, x minus 2. So this goes x plus 2, x minus 2. And here is a sum of two perfect squares. So this is x plus 1i, x minus 1i. So x plus I, x minus I, and all that equals 0. So our solutions are plus and minus 2 and plus and minus I. And so watch for that kind of pattern. Don't let these powers freak you out. You already know how to do this. Here's another example of a problem. This is a cubic. So step 1, set it equal to 0. So x cubed minus 1 equals 0. Whoa, look at this. This is a perfect cube, and this is a perfect cube. We have the difference of two cubes. So we are going to use that pattern that I just showed you a minute ago, a minus b. So x minus 1 times a squared plus ab plus b squared, and there we go. And now I have factored that equals 0. This 0 we can see, well, this one we'll have to use the quadratic formula for, because 1 plus 1 would be 2. I can't factor this normally. So let's go ahead and do our quadratic formula. A is 1, B is 1, and C is 1. So x equals negative b plus or minus the square root of b squared minus 4 times a times c times 1 all over 2a, or 2. So this is negative 3. So what we have is negative 1 plus or minus I square root of 3 over 2, and those are two of your solutions. And the other solution is here. It's 1. So those are your 3 solutions for this, and yes, it's perfectly fine to leave it like this. And if you want to put the I here, you can do that. If you want to split that up, negative 1/2 plus or minus square root of 3i over 2, you can do that, but you can just leave it like this, simpler. There you go. This one's really cool. When we set this one equal to 0, we get x to the 4th minus 16 equals 0. We have a difference of two squareds. So the square root of x to the 4th is x squared, and the square root of 16 is 4, so we have x squared plus 4 and x squared minus 4. Now we can factor these further. This factors to be x plus 2i, x minus 2i. This factors to be x plus 2, x minus 2, and then there's your 4 zeros. So hopefully that makes sense in how to factor a problem that looks like that. The next section in your textbook is how to use the graphing calculator to solve these. So what you would do is put these in standard form. So this would be x cubed minus 4x squared minus x plus 5 equals 0. or set that equal to y, enter in your y equals, treat it like a function, equals y, and put this into your calculator, and then select graph. And then what you will do is look for those intercepts or those zeros, and look for the zeros of this function on your graphing calculator. This would be good to figure out how to do that for those of you who have graphing calculators, how to figure out how to do this on your graphing calculator. Practice it with this. If you remember, if you don't have one, there's some free ones like Desmos available online that you can practice with on the computer. Your textbook says that these are the 3 approximate zeros, approximate answers that you should get. It helps to know what you're looking for as you experiment with this and see if you can find the correct solution. So it is possible to do this using a graphing calculator when you get an equation like this that you cannot factor. I will show you in the future how to solve these, but not yet. You are going to be asked to model a polynomial and find the zeros of these types of things, so don't skip this last word problem, because you will have problems like this, very, very similar. So if you can tackle this, deal with it, and work with it, when you come across it on a quiz or a test, you'll know what to do. In this word problem, we're told that Stacy, Una, and Amir all have the same birthday, but they weren't born the same year. We're told that Stacy is born 1 year after or before Una. I gotta check. Okay. Stacy is 1 year younger than Una. So she is Una minus 1, because she's 1 year younger. Amir is 2 years younger than Una. Right? Yes. So Amir is, since he's 2 years younger, he'd be Una plus 2. Una's in the middle, so we'll make her X. So if Una is X and Stacy is 1 year younger, then Stacy would be X minus 1. And since Amir is 2 years younger than Una, Amir's age would be Una plus 2. Okay, now, just like we did with that box before, we have all 3 of their ages, how they relate to each other in terms of X. Okay, we are told that the product of their ages, remember the product is the answer when you multiply, so the product of their ages was 2,300 more than the sum of their ages. So if we take the sum of their ages, so we add their ages together and add 2,300 to that, it will be the same as their product. So let's use that to set up an equation. The product would be X times X minus 1 times X plus 2. That's the product. Okay, their product was 2,300 more than the sum of their ages, which is X minus 1 plus X plus 2, or 3X plus 1. There's our equation. Now we are going to simplify both sides. So I'm going to go ahead and FOIL this and then multiply this by X. So this is X squared plus X minus 2 times X is X cubed plus X squared minus 2X equals 3X plus 2301. Okay, whew, so there we are with the 2 sides simplified. The next step to solve this would be to set it equal to 0. So I'm going to move this 3x over and this 2301 over. And I get x cubed plus x squared minus 5x minus 2301 equals 0. Whew. This is not easily factorable, so you would want to put this in a graphing calculator. Y equals this, and then look for only, don't even think about imaginary solutions, just real ones. Where would this cross the x-axis? And when you do that, you see that x is 13. So that means Una is 13, Amir is what, one's 11 and one's 14, I think, something like that. Anyway, plug in those formulas we did at the beginning, you get all 3 ages then that way. Whew. Here's another example of a problem you could set up a similar way. We're not going to solve it, but I'm going to show you how to set it up. What are 3 consecutive integers whose product is 480 more than their sum? So to get 3 consecutive integers, my first integer I'll just call x. Okay, then consecutive means what would come next? Well, it's this plus 1. And then the one that would come after that is x plus 2. Those are my 3 consecutive integers. This plus 1 more, and that plus 2 more. That's 3 in a row. This represents their product. If I multiply that out, their product is 480 more than their sum. So add 480 to their sum, and their sum is 3x plus 3. And that's how we'd set up our equation. So we would multiply this, x squared plus 3x plus 2 times x is x cubed plus 3x squared plus 2x equals 3x plus 483, and set it equal to 0 and solve, and there we go. So this is the tricky part. How do you get these 3 expressions and then set it up? And yeah, this is Algebra 2. Welcome to Algebra 2, everyone. So that is section 5.3, whatever it is, the next one on polynomials. Keep working with it, keep working with it. It does pay off and it does get easier. And I will see you guys next time. Bye for now.